So before we bring Brett and excuse me, how about now? Good? No? Hear me all right? Okay. So before we bring Brett and Frank up for this great session, I just wanted to remind everybody that we do have 2 other breakout rooms running in unison. So over in Winrose 1, we've got the web assembly session, and then over in Osaka, we have the data science workflow session. So this will be a great session with Frank and Brett, but just want to make sure everybody's in the right spot, and feel free to bounce into the other breakouts after the session is over. So thanks very much.
All right, thanks. Hello, everyone. Hope you all enjoyed your lunch, took a little bit of time to connect, to socialize with the other participants. Thank you very much for coming to the Edge Computing session. My name is Frank Zdarsky. I'm part of Aaron Boyd's Emerging Technologies team in the Office of the CTO. I actually joined Red Hat 2014 before I was leading a mobile network R&D at NEC, so I was actually at the customer side of Red Hat. And at that time, my team was looking into re-architecting NEC's mobile network functions to work on AWS Cloud. And that was a very fortunate timing because just in the following years, there were 3 disruptions hitting the telco industry. The first one being moving from being hardware-defined to software-defined and cloud. The second one was the transition to basing your operations on open source technologies. And the third one was actually edge computing. And you already see that these are themes that then followed me as I joined Red Hat. Initially, when I joined, I was translating between our telco customers, open source standards communities, and our Red Hat engineers. Then I built a team that was working with incumbent network equipment providers and service providers in the telco industry that would be strategic for Red Hat. And my team was actually co-creating, as you've heard before, with these customers and partners to enable OpenStack and OpenShift cloud platforms for 4G and 5G workloads. And right now, I'm leading edge computing in the Office of the CTO, and the goal is actually to drive convergence across our portfolio from a technology perspective and address gaps in the portfolio. Brett.
All right. Thanks, Frank. Brett Thurber. I've been at Red Hat for close to 12 years. I came over from Dell. Prior to Dell, I did some consulting work after I finished my service in the Air Force. When I came to Red Hat, I was initially hired to write reference architecture. So I went into product marketing. And that eventually led to roles in engineering where we were doing solution development and doing a lot of end-to-end portfolio testing to make sure that our products work together and that when we wrote these reference architectures that they could be consumable by our customers and not break all the time. So that was a very challenging life cycle to go through. When we had a new version of OpenStack release, we had to make sure that OpenShift worked on top of that, for example. So that all transitioned over into leading some engineering teams inside of Red Hat to develop various products and tools. Today I work in ecosystems engineering and I lead the partner acceleration team there. And basically the whole purpose of our team is to work engineer to engineer with our partners to make sure that they can enable their solutions on our platforms. So we work with very low-level things like kernel modules and drivers, and we'll get into that a little bit later about how we're strategizing our ability to enable those partners in cluster and on our other platforms. So, Frank?
Thank you. All right. To ease you into this topic, it's important that we talk about this tension between edge computing and cloud computing, right? What is edge computing? Is really general purpose compute using cloud-like processes and tools, but that happen outside of the data center, outside of the cloud, right? It's happening close to where the data that you want to process is originating and where you need to take actions, right? Where you're engaging with customers or where you have any type of physical presence or asset, really, right? And edge computing can have many locations. What you see there is service provider edge. It's what telcos would be typically interested in. as enterprise customers, you would be more interested in what we call enterprise edge. And there's a fundamental, let's say, distinction line called the last mile access. What does that mean? It's basically fiber, copper, satellite connectivity, cellular connectivity. It's network that in many cases becomes a bottleneck. And this is why for everyone looking into edge computing, network is super important. Now, you might think, I'm struggling already to move my service into the cloud, or I have just moved my service into the cloud. Why on earth would I now move things back out to the edge again? And there's this tension where you're saying, I'm moving services to the cloud. Why? Because I'm hoping for, of course, to outsource, but also to have better economies of scale, resource sharing efficiencies, etc. Right? So you move as much as possible your services to the cloud. However, there are constraints. There are services that, for one reason or another, you cannot move to the cloud and you want to move farther to the edge. And that's typically because you need more control, right? You can't have your factory connected outside for security reasons, right? You can't rely on the network because your operations cannot stop just because the network goes down, right? And you may suffer from poor network connectivity. Network is expensive, it's slow, it's not typically available. So these are kind of tensions, and I would argue that every company that has physical presence still, and most of you do, or has physical access, sooner or later wants to look into the topic of edge computing. There are typical journeys how our customers get to edge computing. I want to pick 4 typical examples. And I'm naming an industry here, but really you can swap out the industry in many cases. The first one is, as a supplier to the telco industry, right? We have suppliers who, over time, build up a portfolio of products for the telco industry, and they build it on their custom hardware. They built their own operating system, their own hardware enablement, right? Then they added another product with a new operating system variant and another one, and then they had multiple generations, and sooner or later that this combinatorial explosion of operating systems that they had to maintain. And they realized, I don't have resources anymore to do my actual core business of the services I want to innovate on. And so what they want to do is to re-platform to a general purpose Linux distribution. So somebody else takes care of the security issue. Somebody else takes care of them for the hardware enablement, and they just focus on services, and they use that opportunity to modernize, to get to microservices, etc. The second customer journey I want to talk about is we have customers from the manufacturing industry, and they have worldwide production plants, and they still separate their operational technologies, and their IT. Right? And there's this trend to actually converge these two, because why would I create a double infrastructure? Right? Why do I have double teams? And the same thing actually happened in telecommunications. It was just called network technologies and IT. And it turns out the technical challenges are actually not the big problem, because the platforms that we sell have the capabilities to run extremely challenging workloads of your OT or of your network technologies. It's typically more a cultural and organizational challenge, right? How do you get teams from different parts of the organization to work together with the same tooling, right? With the same way of operating networks? This was typically more the challenges of these customers. And of course, the brownfield, because they needed to integrate brownfield systems and automate them. The third example is retailer, right? One of our customers is basically looking into modernizing the IT infrastructure in their stores. And why do they want to do that? Because they realize that the systems that are running their cash registers and their logistics, etc., they couldn't evolve very quickly. So they wanted to modernize to a system where they can rapidly push out new versions of the service to those stores. But that's improving internal operations, right? As soon as they were able to innovate on service and push them out to their stores, That was whetting their appetite. And so the next thing they wanted to do is say, hey, if I anyway have IT in all these stores, can I leverage that to better engage with my customers, to better gain insights into my customers, so doing things like, recommendation systems on, closing, right? You stand in front of this smart display and it just shows you in that display with different closing on, right? Fourth use case is manufacture of autonomous vehicles. So as you'll see at the edge, hardware is super important. You don't deploy general purpose hardware. You choose hardware to match your use cases, right? And this customer basically said, I need to do video processing at the edge and take actions on any features, any problems identified in my production chain, right? Quality control. So I hope that you have a chance to find yourself in any of those four prototypical use cases. If you have other use cases that don't fit into these categories, I'd love to talk to you after the session, so please come see me. So why is the adoption of edge computing just ramping up very slowly? Some are very fast, and some companies are adopting edge computing very slowly. And that's, I would argue, because there's this perception of that edge computing is much harder than cloud computing, right? And so I put up this table here, and I don't want to go through it in every detail, but just mind you that I'm contrasting the edge and cloud, so I'm dial up the contrast, right? I'm exaggerating in some of these cases. And there are many, many reasons, and I only put a selection up here, right? So an obvious one is capacity planning, right? On cloud, you can scale your capacity exactly to the demand plus some safety margin, right? So basically follow your demand curve, right? At the edge, you can't do that because you can't, in thousands of locations, just dynamically add compute, right? So the challenge there is to dimension for your use case. And as I hinted to before, demand grows over time. So once you can have a certain capability at your edge sites, suddenly you want to do more and more. So that's one of the challenges. The other one is hardware. As I said before, you don't want to run any type of workload on a general purpose machine. There are reasons why you have machines that have more memory, less memory in relationship to the CPU, that have GPU acceleration, that have network acceleration, or tensor cores, or whatever. And that's really because if you think about your production cost, your performance per dollar, or your performance per watt, you can't get to good production cost without right-sizing your hardware, right? You can select from different cloud instances with your cloud provider, and the cloud provider will ensure that they are reasonably complementary, and the cloud provider will enable that hardware for you. At the edge, of course, you have a huge variety of vendors to pick from, and it's either the customer, you yourself, who have to do the hardware enablement if you're a systems builder, or you're basically outsourcing it to your hardware supplier or to your operating system supplier. This stuff is challenging. That's why, we have a session after this one talking exactly about hardware enablement, how we do that. And also I have Brett here with me to talk about how operationally all of this works together. Other aspect, hardware provisioning. On the cloud, an API call, you have the hardware, right? The virtual hardware. In practice, it's a truck roll. So you really need to think about how do I actually deploy edge compute to the different locations, right? It's a geo-distribution problem. The other problem is cloud providers have SMEs on site. In this case, you typically have no personnel on site, or if the personnel is on site, they're typically non-technical, right? So you can't expect them to do any type of maintenance. There are many, many other differences. So for example, network connectivity, I mentioned that one already. Security, and again, my colleague Luke Heinz is going to talk to you about secure supply chain if you're interested in this. And then finally, and in my view, most importantly, is your developers actually developing the services. And there is this distinction between those developers who grew up on cloud, right? And Kubernetes and Kubernetes-related tooling and lambdas, so functions, are what they grew up with. At the edge, you have embedded systems, folks. They use completely different tooling, completely different culture. And the challenge is really, if you have a world where edge and cloud compute converge, how do you deal with that situation? So, in order to ease this problem, right, what Red Hat has always been doing is to say, hey, with our Red Hat OpenShift, we have the capabilities to deploy workloads, Kubernetes services, anywhere, right? The hybrid cloud idea, you can deploy it on any of the public clouds, in your data center, and we've basically been working to make the footprint smaller and smaller, so you can have 3-node server clusters or a single server, and OpenShift will run everywhere. And that means your developers can just develop once, and they can be confident that no matter whether they then run one part of the service in the cloud and the other one in your factory, it will all just work the same. And the management above it, the ability to observe what's going on with your services and to roll out new versions, is also uniform. So what's new at Red Hat is that we're actually looking in what's called field deployments of devices. You've heard about the drones, right? Or the satellites that we're doing. We're working with car manufacturers. But it's not only these vehicles, it's also IoT gateways. It's point of sales terminals or displays in train stations, right? These are all devices and they're in the field, and that also means they suffer from network, they suffer from people touching and fat fingering these devices. And so the environment in which you deploy to is very, very different. And so what we're doing in Red Hat now is basically to say we have created a variant of RHEL or tools around RHEL, our Red Hat Enterprise Linux, that ensure that the hardware enablement that we do for you and the way you run workloads works also on these edge devices, right? On smart displays in your stores, on your cache registers, whatever is you deploy in the field. And you can do that the traditional way, RPM packages, right? Traditional software packaging on Linux, or containers, or, and that's what has been mentioning before, Microshift is, if you want a runtime, an option you can deploy on these devices to say, I actually also want to run Kubernetes services there, and what you gain then is exactly this consistency from the cloud up to the far edge. Okay. I'm going to go briefly through 3 slides. I promise I don't go into all of these technical details, but just to give you a taste of why we're doing some of these things, right? So think about your phones, right? Your iPhone or Android phone. Think about Alexa, your cable box at home, etc. These do not work and they do not operate like a server. And you do not expect any technical expertise you just buy them and plug them in, and maybe you do some mobile phone thing to register their box, and that's it. Right? And we want to have the same experience no matter what your edge computing workload is. And that's actually what we did. So RHEL has now these features which essentially look like you're building your own mobile phone operating system, right? You can define exactly what are you going to deploy, which operating system, which hardware enablement, you define it, you put your workload on top of it, and you bake what's called a system image. And then all the hard part that Apple or Google or others do, we take care of for you. So how do I do over-the-air updates? And even over unreliable networks, right? The network is maybe sometimes not available, it's slow, and we can just send the difference between your old and new version, and we can do secure updates, right? What happens if you update and suddenly you pushed a bad change, suddenly your system doesn't work anymore, right? In a cloud, you can always recover. In a data center, you can always recover. In the field, you cannot recover. You would have to send some technical person. So we have the possibility built in to define a watchdog that says, oh, I've updated to a new version, something broke, and I automatically roll back, and I'm still operational, right? So all of these hard things, our RHEL team has actually solved for you. The next part is FIDO device onboard. Again, without going into the details, FIDO device onboard is a way to optimize your supply chain, to say, I want to order 1,000 devices from my hardware supplier. I'm going to tell the supplier, please deliver these devices directly into the stores where I need them and plug them into the network, plug them into power, and leave. And everything else, the secure onboarding of that device into your management system, FIDO takes care of. Microshift. As I mentioned before, you have these edge devices, you can deploy traditional workloads. You may want to deploy Kubernetes workloads though, again, for this level of consistency. Microshift is a very, very small footprint Kubernetes runtime if you want. Right? So you can take a Raspberry Pi and you can, of whatever, 2 GB RAM and run an AI workload on top of that using Kubernetes services, right? It's that, can't promise that like if we were to productize it, that it stays that small, but that's what we, for example, achieved. And what you can do is basically you take this operating system image and you plug Microshift into it. Sorry, it's hard to, you were asking a question or?
Oh, yes. Architectural-wise,
yes.
I know to make it more lightweight. K3S is lightweight but different architecture.
Yeah. Yeah.
Okay.
Right. Okay.
Hey, think fast.
All right.
Excellent. So please.
No, architecture-wise, right? I mean, I know Microshift is lightweight Kubernetes, right? And we know Rancher, they have K3S, but it's different architecture. It's not Kate, right? To make it so lightweight, so what's the underlying architecture look like for Microshift?
Right. So you mentioned K3S from Rancher and SUSE, right? A small footprint Kubernetes distribution. Microshift is our small footprint Kubernetes distribution, like using a lot of the OpenShift features like hardened security, etc., right? And of course, other vendors have their distribution. What is differentiating, what we took care of, we laser focused on this edge device use case in production deployment. So there are architectural decisions that we took that make more sense in our view in a production deployment. If you want to have security certification for your device, if you want to do patch CVEs, etc., that are easier in that type of architecture, whereas K3S originally came from a developer use case and then extended into edge use cases. So people thought, hey, it's actually quite handy, I can use it for edge use cases as well. And you notice this in the architectural choices that they've made. But in a sense, it is a similar Kubernetes distribution in the same class as K3S, KOS, microK8s, etc. Yes. Did that answer your question?
Yeah, thanks.
Excellent. Yeah, so the key point is here, Microshift is basically building on top of these RHEL features that I talked to you about, right? So you can leverage the ability to roll back your system. You can leverage FIDO device onboard. Microshift doesn't do any of this. Just when you decide I need to run Kubernetes services, you optionally embed Microshift into your system image, and then you can use it. You can deploy the same workloads with the same tools as on the big OpenShift or Kubernetes clusters. So that's the idea of that. Next, let me hand it over to Brad because we really need to talk about the hardware enablement and how to operationalize this.
Thanks, Frank. Yeah, the important part of Edge, obviously, is being able to bring up the devices. In order to bring up the devices, we need to have the proper kernel modules that enable these devices through the operating system. So we work very closely with partners in our team, validating and verifying, helping them adopt our technologies. We provide a set of tools for them to help them adopt, being able to load their kernel modules. There's really two ways that you can load kernel modules. One is in tree and one is out of tree. So our tools are really focused around out of tree. And why? I mean, in tree is always better. The problem with in tree today is it takes anywhere from 12 to 18 months submitting your kernel module, and Linux upstream space for it to get approved, accepted. That then gets pulled into downstream RHEL, that gets tested, that gets certified, and that becomes part of Core OS, and so on and so forth. So that's a very lengthy process. Our partners that we're working with are very aggressive on their timelines. Time to market their solutions is critical. And in order to enable their devices on our platforms, then we need to have a way to be able to enable those in, you know, the kernel itself running on that platform using out-of-tree drivers. And so, you know, these devices could be many things. They could be FPGAs, they could be DPUs, they could be IPUs, they could be P2P adapters. They could be a host of different things out there. So you'll get a chance to see a little bit of this hardware in the next session with Chris and Steve, and we'll talk a little bit about that more towards the end of our presentation. So obviously the goal here is time to market. We want to help them adopt our platform and our solutions quicker. So as we mentioned, there's a couple of ways of doing that. We provide some tools. One of the benefits of consuming Red Hat technologies is a tool known as a driver container toolkit. And what this does is it provides us a RHEL UBI-based image with all the necessary kernel versions of the compiler tools needed for a particular kernel that's running. We follow along very closely with Core OS, so anytime we detect a kernel update that comes through, we spin a new version of our driver toolkit container, which our partners can then consume, and then they can rebuild their driver containers and their kernel modules to match. This becomes important when we talk about upgrades. So when you're doing a cluster upgrade, so let's just talk about hub and spoke for a minute, and as an example, you know, if I've got a centrally managed cluster and I've got spoke nodes / clusters at the edge that I'm managing through that centralized management cluster, our tooling that we're working with is meant to be deployed in the centralized management server, but we're able to detect and monitor what kernel version we're running on the edge devices. So, you know, rolling upgrades is usually something that you hear in the industry. Telco is a good example where they carve off a specific amount of resources that they're going to upgrade at one single time. And so it's just, you know, it's a continual rolling upgrade over time. So one of the things we had to build into some of our tooling, and we'll talk about that, is being able to support multiple versions, multiple kernel versions, and also driver containers with those kernel modules for those kernel versions. It becomes very important because in any ZStream kernel update, if you're using an out-of-tree kernel module, it's very possible that if you update your kernel to the next version, it's going to break that out-of-tree driver. And we don't want to cause an outage in the system. We don't want to cause an outage at the edge. That becomes very difficult to overcome. So as part of our solution, we're doing what we call pre-flight checks as part of the upgrade process. So we're looking for incoming kernel versions. And based on the custom resource that's defined for our operator, we will look for an updated version of the driver container for that. If it's available, then we'll pull that in as part of the upgrade process and upgrade that kernel module. We do that to prevent any outages, so it's more proactive than anything else. If we're not able to find that and it doesn't work, we fall back to what we call build config in OpenShift. So this is an advantage that you don't have in just vanilla Kubernetes today, is that we will look, if we can't find that driver container, then we will rebuild the existing kernel module with a updated version of the driver container, upload it to the registry that's configured for the cluster, and then deploy that for the new kernel version that's incoming. So we've got some safeguards that we've built in for that. We talked about driver toolkit container. We talked a little bit about, you know, what happens when we need to load one of these things. There's really the use cases that we're working on and targeting today are around day 1 and day 2. So for day 1, there's a technology called OS tree layering, which was introduced in Fedora 36. And what this does is it basically allows us to layer in a driver container with a kernel module as an overlay on top of the operating system. And what this does for us is it allows us to, as you're deploying you know, your system, it allows us to inject this out-of-tree driver kernel module, and it allows us to enable that device or set of devices in that platform. Yes, we can handle more than one kernel module for different devices. So it works very closely with DTK and OS tree layering. I'm going to show a short demo of what we've done. It's a very early POC, so I want to set the expectation that this demo is not highly polished at all. So just bear with us as we work through it in a few minutes. But we just finished it up this last week, by the way. So this is new technology that we'll be, releasing generally available in the future. All right, and then we have what we know as day 2. So we put together an operator. This operator is called Kernel Module Management Operator. Today it's part of upstream Kubernetes in the SIG node space, and that's obviously where we work with our partners very closely. Anyone that's willing to collaborate and contribute is more than welcome to, but we have several partners that we're working with upstream to develop this operator. And the whole idea behind this operator is to, as I mentioned, to manage your out-of-tree kernel modules for the needed specialized devices in the cluster. So it also works in conjunction with DTK. Talked a little bit about the custom resource where you define what this kernel module is, where it needs to point to for the driver container and so on. And for each module, we can create 2 daemon sets potentially. The first one is going to be for the driver, and the second one, we also provide the ability to deploy and manage a device plugin. So, that basically enables Kubernetes scheduler to see and know about this device, to schedule workloads against it. A lot of our partner operators, they've managed their own device plugins outside of KMMO, but we wanted to provide this as a feature going forward. Some other features that I don't have listed that I'll mention as well is support for secure boot. So let's say, we've got a TPM on a server platform somewhere, we've got secure boot enabled, we've got our key stores configured, we want to basically go through an upgrade, and we need to re-sign this kernel module, as part of the driver container. Our operator will detect that, and we will automatically sign that kernel module with the supplied keys and deploy that as part of the upgrade process. We're also looking at adding support for firmware updates as well for specialized devices in cluster. So we're working on adding that to our CRD as a feature. Hopefully that's going to be in our official release going forward. We've got a little more POC work to do on that, but it's getting really close. All right, so we talked about DTK. That's the short term acronym for driver toolkit container. We talked about kernel module management operator. We talked about upstream Kubernetes, and now we're working on releasing this at some point downstream. So basically we have a solution for day 1 and day 2 that implements management of those out-of-tree driver containers. All right, and this is just really a graphical representation of what I just described. So if we look here, we'll notice that our operator resides in the middle. We're managing these driver containers. We're looking for specialized hardware in the cluster. And you might ask yourself, well, how do you know? Well, we have another operator called Node Feature Discovery that allows us to label nodes in a Kubernetes cluster to know if there's going to be a specialized resource on that. So we're not just peanut butter spreading, loading these driver in daemon sets across all the nodes in the cluster. We're looking for specific devices in the cluster. So those vendors will generally have a PCIe hardware ID that we're looking for, and based on that hardware ID, then we label the node, and based on the CR configuration that we have, it'll go out and look for that label on the nodes, and then it'll know what daemon set to load for that special resource in the cluster. All right, that's a lot to say. I'm going to pause real quick. Are there any questions around any of that? Did I put everybody completely to sleep with my monotone voice? All right, it's post-lunch, carb hangover, I get it. It is what it is. So let's switch over to some demos. So we've got a couple of demos that I want to show. These demos are going to be around, just like I say, very early POC for the OS tree layering. And then we want to show a little bit of early work with our kernel module management operator. We do have a question. Lauren. toss. I don't know, maybe. Yeah.
Okay.
Yes.
You mentioned you're identifying modules for a PCIe ID.
Yes.
That could be spoofed. How are you guaranteeing that you're getting the right?
Well, we rely on our partners to provide us with a PCIe ID. So my suggestion would be to look at node feature discovery in upstream Kubernetes in the SIG node space. By the way, my team is just taking over responsibility for that as well. So, you know, I mean, it's like anything in life, there are no guarantees, right? But at the same time, it comes down to limiting access to those devices and the hardware. So,
So you're taking over the PCIe side. Are you going to require something down the road that requires a multi-factor authentication for those PCIes on the devices? Or are you going to create a standard so that you can guarantee, hey, this is legit, Intel has signed this, and it's on our side, and we can see that it's good?
that's a question I think we would have to collaborate with our partners on, you know, to come up with a standardized solution. We need to explore it a little bit. I don't have a good answer for you today on that outside of, you know, if you don't have control over your hardware, you know, it's not secure, anything's possible at that point. You know, anybody could walk in with a USB key and do what they want to do. And there's got to be some level of physical security there before you even get to the, you know, the OS layer of things. So potentially, I mean, one of the big topics that's going to be coming up, and you'll probably hear more about this in the future, is going to be confidential computing. And confidential computing is basically where we're ensuring data protection, you know, for each process that's running in the cluster. And, you know, we'll see what it turns into. So, okay.
I have a quick question. So does SRO go away?
SRO, that's a really good question. I haven't talked about the special resource operator. There's a history behind that. And the reason why we switched from using SRO to KMM is because of two things. SRO was built focused around Helm charts and using a state machine to help manage instantiating a complete solution into the cluster so it would maintain all the life cycle of a partner solution in the cluster. We felt that wasn't scalable or supportable. It means that Red Hat would have to ship all of the partner Helm charts and RBAC configurations and everything. So, you know, if an end user calls us, we're going to be like, oh, I'm not entirely sure. So basically, if we build it and ship it, we have to support it. So it became unsustainable from a support standpoint. The other issue, if folks in the room may or may not know, is the state of Kubernetes security has been a big topic this year. And so with that particular operator, it requires elevated privileges to run in the cluster to be able to load Helm charts. There were no restrictions on where we could load these Helm charts from. There was no way to guarantee that someone couldn't just use this to, as you know, politely mentioned, spoofing, you know, a solution into the cluster, and then now you have ultimate control over everything. So we ran into certification issues with partners using SRO as well. So that's why we kind of put the brakes on that, and we said, okay, SRO is tech preview today. We don't want to open up a can of worms by releasing that as a GA solution. We should probably do a start, stop, continue exercise, and now we've developed KMM as a replacement for SRO. I hope that answers your question.
It does. Yeah, no, thank you. That actually makes sense. And so this is not specific to Microshift, right? This is all things OpenShift.
That's correct. Yeah, it is not particular to Microshift. Now, we could partner with Microshift and help in that space for loading out of tree drivers if needed. You know, one of the requirements from our solution, we talked about hub and spoke, is not deploying our operator on all the spoke, you know, edge devices because of finite resource availability. So that's
all about small footprint.
Exactly. So that's where we get into, you know, reducing our footprint. We're just deploying what we need on those nodes or on those edge devices and managing that centrally in the management cluster. So
let's see demos, shall we?
Yeah, we're quickly running out of time. So my apologies. Any other questions before we try to execute some of these demos? Okay. Can we switch the screen over to here. All right. So hopefully this is going to show.
Yeah.
Like I say, my apologies. This is a very, this particular demo was recorded just a couple of days ago. It's very, the font size is very small. I might be able to zoom in a little bit. I'm not sure if it's going to help or hurt, but let me see. It may cut some of this off. That's about as good as we're going to get. So, all right. So just to get started, this is the OS tree layering demo. Let me pull up my other side here. Okay. My mouse has disappeared on me. There it goes. All right. Okay, here we go. Let's get started. So in this particular demo, what we're showcasing here is applying a new layered image against the worker nodes in this particular cluster that we're managing. This image contains a simple KMod kernel module that we use as an example for doing our smoke testing when we're doing our builds and releases. And this kernel module was built using DTK, so just FYI. And we've got a little bit of, for whatever reason, it's not playing. Let's try that again. I'm going to kind of skip ahead a little bit here. So I apologize if you can't read this. This is going to be very small and difficult to read. We can provide these demos post conference as well for those that may be interested. So basically what we're doing here is we're configuring our layered image. Once our layered image is available, then we start working on the deployment in the cluster. We'll see on the right-hand side shortly. See if I can get over there. There we go. This is just an example of what we're pulling from. So we have our image located in our Quay repository that we're going to be pulling. All right. And now we are applying our layered image. And from here, you will start to see shortly worker nodes, basically unscheduled resources, go offline and then come back online again. And we will eventually get there. Okay, there we go. So now this is where we're unscheduling. Basically what we've done here is we've used machine config to apply this layered image. And once that layered image is applied, then it reboots the node. And at the end of that reboot, once the node's back up again, we check to make sure that that kernel module is loaded. So I'm going to skip ahead a little bit more here, and soon we will be at that point. Okay. So in this particular scenario, we're looking to make sure that the simple KMod module loaded as part of the post reboot, which means that our layered image was applied using machine config. And so like I say, it's a really basic POC that we put together right now. A little bit of dead space here and there while we were waiting on things to complete and compile, but that's it basically. That's a short look into that. So next we're going to take a look at kernel module management, and this is also going to be an early POC that we put together. Let's see if I can get this moved over. Maybe. There we go. Okay. The first scenario that we're going to walk through is going to be using a pre-built driver container. The second scenario that we're going to showcase is going to be using in-cluster builds that we talked about earlier. So let's get started. Hopefully you can see this a little bit better. So right now we're just taking a look at, the module CR configuration that we have. So we have two that we put together here for module A and module B. And we're just showing that we've got 2 of those CRs configured. Okay, at this point, we're applying the CRs. And from here, it's going to begin the loading of these modules into the cluster as daemon sets. I mentioned I'm going to pause here. I mentioned the node labeling. So as we talked about, looking at which nodes we want to load these kernel modules onto, this is what we're doing here is just showcasing that we're labeling a node in the CR configuration. We kind of breeze through it pretty fast, but you'll notice that there was a label section in there. It's looking for a particular label. So that's what we're applying here. All right, and so on the right-hand side, you can see that we're loading these daemon sets onto the nodes. And that's pretty much it using the pre-built driver container images. The next demo is going to be a little bit longer because we're actually pulling things in to compile the driver container for, and then we're uploading that driver container image into a registry, and then we're deploying that into the cluster. So let me pull that up for us real quick, and we'll walk through that. We're just about out of time, by the way, so yeah. This will, I'm not going to pause it, I'm just going to let it run. So, all right, so if you notice that the CR for this kernel module is quite a bit different, we've got a build section in this one where we didn't have that in the other, so we specify what we want to build and what we want to deploy. All right, so we're going to apply the CR. And at this point, we're just going to look at some logs, and it's going to show us the actual building of the driver container. Once that's built, then we're going to upload that to a registry. We're almost out of time, by the way. We have about a minute left, so my apologies. We knew we were going to run over a little bit too, so. Yeah. All right, so we're basically downloading all the necessary tools to compile for this particular kernel.
So maybe I can use this opportunity to emphasize one thing that may have gone a little bit missing. We talked about this consistency, right? We want that you have a development and operations team to whom it looks the same whether you develop on cloud, the near edge, or on these other devices, right? I mean, the beauty of this approach that Brad is showcasing is that all of these hard problems of updating drivers is actually hidden behind this common language of the cloud, which is Kubernetes, right? So if you have a Kubernetes developer, if you have a Kubernetes operations team, all of this would look super familiar to them, right? So
we're compiling the module here, so go ahead, Frank.
So as I said, it's one of the goals here of this session to show you the opportunity behind edge computing. So we've looked into the different user stories and user journeys, right? Hope you can identify yourself with those. And then again, as I said, a lot of these edge computing problems seem hard, and we're working very hard as Red Hat to actually make them easy for you, as easy as cloud, right? From a development perspective, from an operations perspective, but most importantly also from a hardware enablement perspective, because unless you enable this special hardware, you're not going to leverage the production cost efficiencies of performance per watt, performance per dollar that you need to get to if you want to be successful at the edge.
Switch back now to the other screen. Yeah, just to wrap up, we finished building, compiling, uploading the driver container. We then deployed the kernel modules in the cluster, and that was it for that demo. So next slide, just to wrap up, I wanted to call out Chris and Steve's sessions next. So they're that's not working for whatever reason. Can you go to the end slide? So we kind of built a foundation talking about Edge. We talked about getting that part of it enabled at the, the hardware layer. We can make it now usable, and it's configurable, and now we can put our computational workloads on that. So just to wrap up here, I think you're going to enjoy Chris and Steve's demo, because it's going to be a heck of a demo with some dedicated hardware focused around what computational computing, all of the pieces that go into the edge and the potential AI space there. So, Frank, did you have anything else you wanted to add?
Yeah. So please, if you have any more questions, see us after the session, or just reach out, and we're going to leave our contact details on there on the next slide.
Yeah.
Excellent.
Thank you
very much for
time.
coming.